Hello, everyone. Let's get started. Thanks for joining our HTC Vive eye tracking SDK webinar. My name is Corey Corvus. I am a developer relations engineer at HTC Vive. We announced the Vive Pro Eye at CES 2019 last year, and eye tracking is a new and exciting technology. I'm a big believer that foveated rendering will be an important application of eye tracking and will be found in more and more headsets in the future. Whether this is your first time learning about eye tracking or variable rate shading, or you've had some experience with this, we'll be covering some important topics about their uses to help everyone get started. Here's the agenda for today. We'll go over an overview of some eye tracking use cases and high-level information. Then we'll dive into the downloads that will be required to get started. Then we'll talk about the runtime, the calibration process. Then we'll get into foveated rendering integration. After that, we will discuss recording eye animations. After that, we'll discuss the SDK in a little bit deeper dive, a little bit more technical. And then finally, we'll have some demo videos to show off the functionality. And we'll end with a Q&A with any remaining time. This is the Vive Pro Eye. We created this to add eye tracking functionality to our Vive Pro headset. We developed this in a partnership with Tobii, which is a leader in the eye tracking space. One of the ways you can identify the Vive Pro Eye as opposed to a normal Vive Pro is you can notice there are blue rings around the cameras on the HMD, and those are only found on the Vive Pro Eye with eye tracking. We believe that eye tracking is going to be a foundational technology that will be driving richer experiences in VR. One of the main functions is the fast foveated rendering, which is made possible with the NVIDIA VRS variable rate shading plugin. We believe this will present new opportunities for revenue, user insights. You can leverage existing content to add eye tracking functionality, and this will add a greater purpose to your content. Users will be able to find more engaging. Let's talk about some of the use cases for eye tracking. The primary use case will be foveated rendering, which we'll discuss further in the talk if you're not familiar with it. Another useful use case is analytics. This is popular for training and enterprise applications. Training is also a popular use case for eye tracking. And for games and game content, eye tracking is going to be useful for aim assist, whether you're shooting or throwing an object. You're generally looking where you're going to be targeting. Similarly, object and UI selection can be helpful with eye tracking, making it easier to pick objects just by looking at them, or scrolling text or menus by looking at the edge, the bottom of the screen or the side to scroll smoothly. And finally, a great use case is expressive avatars. This really helps bring avatars to life in VR. You can really have animated eyes, which makes it much more expressive. Let's talk a little bit about the requirements for using eye tracking. Today, we're going to be talking about using eye tracking with Unity Game Engine. We also provide support for the Unreal Engine. And if you're interested in that, we'll try and share a little bit of information at the end. But mostly, I would suggest looking into the forums for information on how to access and use the Unreal Engine plugin. So to get started, there's separate requirements for just eye tracking, and then some more specific requirements if you would like to run foveated rendering. First, we'll cover the eye tracking requirements. You will need Windows 8.1 or later, 64-bit. You will need admin privileges to run the eye tracking runtime. You will need an updated version of SteamVR which is 2018 October release or later. You will also need the eye tracking runtime, SR runtime, and you will need Unity 2017.4.17 or newer. And this will work with the Vive HMD with eye tracking. For foveated rendering, there's some more specific requirements. Specifically, you will need an NVIDIA Turing Series GPU. This will provide support for the variable rate shading, which is required for foveated rendering. Generally, the RTX 20 series cards have the Turing architecture. You'll also need DirectX 11 on Windows. You'll need a NVIDIA driver that's been updated, 430.39 or later. And you will also need Unity 2017 or newer. Let's talk a little bit about the downloads, where you can get the plugins and SDKs. Developer.vive.com will be your primary resource for access. From developer.vive.com, you can get access to many of our SDKs. The Vive Wave SDK is our mobile all-in-one device SDK for Android devices. We have a number of headsets, including the Vive Focus, Focus Plus. A number of other headsets are available in China that all use the Wave SDK. The Viveport SDK is our Vive Store SDK, and that provides functionality for DRM, achievements and leaderboards, and publishing on our store. And the Vive Sense SDK will be where you can find our other SDKs for eye tracking, hand tracking, audio, etc. If you clicked on the Vive Sense SDK, you'll find the eye tracking SDK is one of the options available, and you'll want to click on that to download it. Before you can download, you'll have to agree to our license agreement and developer privacy guidelines. We find this is very important to ensure the privacy of the users. And while you're here, you'll download the Vive SR Anipel installer for the runtime and the SR Anipel SDK for the eye tracking SDK. If you are interested in foveated rendering integration, we have that plugin available on GitHub and the Unity Asset Store. And if you're interested in recording eye animations, I strongly recommend this plugin on GitHub titled Unity Runtime Animation Recorder. And we'll talk about this later in the use of recording eye animations to be able to play back on avatars. Let's talk a little bit about the runtime, which is required when using eye tracking. The runtime is installed separately from your application and has a little robot head icon. Once you launch the SR runtime, the icon will appear in your notification tray, and the eyes will light up orange-red when it's in standby, and they will light up green when eye tracking is in use. And if you right-click on the notification tray icon, you can find out more information about what version of the runtime you are using and the firmware version of the cameras. The first step to using the eye tracking is calibration. This is required for every user to accurately track their eyes. The calibration is a quick 3-step process. The first step is to align and adjust the HMD so it fits perfectly on your head, and so your eyes are clearly in the center of the lenses. You will then rotate the IPD knob, which is found on the right side of the headset, and the slider underneath the image will move when you rotate that knob, and you will want to center it in the box. And the third step is to follow the blue dot. And you will do this by following the dot with your eyes. You don't need to move your head to follow it. And once that's completed, you'll have finished the calibration successfully, and you'll be able to look at any of the dots on the post-calibration screen and they will light up. and we'll show a demo video of this at the end. Let's talk a little bit about variable rate shading. NVIDIA's variable rate shading, VRS, is a fundamental technology that is required for eye tracking and foveated rendering specifically. The variable rate shading is what allows you to change the pixel shading rate for different regions of the screen. There are coarse shading rates, which is the normal 1-to-1 render resolution, as well as lower render resolutions. Super sampling is also available, which increases the render resolution. Generally, you'll be doing coarse shadings in the peripheral and blend regions of the foveated rendering, and you'll want to super sample in the foveal region where the user is looking to increase resolution. 1:1 is the normal shading rate. 2:2 is 1/4 shading rate, where 1 pixel is spread out over 4 pixels, and that increases, etc. There's 3 main algorithms that you can use right now with variable rate shading. One is content adaptive shading, which reduces the shading rate in regions that are slowly changing in color. Motion adaptive shading, which variably decreases shading rate of moving objects. And finally, the one we're interested in today is foveated rendering, which reduces shading rate in areas away from the viewer's focus in the peripheral region. And if you're interested in more on variable rate shading, I strongly suggest checking out NVIDIA's blog. Some of the benefits of variable rate shading are primarily to gain performance. As virtual reality developers, we're always battling and struggling to improve the performance of our applications. It's much more important in VR than it is in a normal application to hit your target frame rate. And so the way variable rate shading benefits is that it reduces excessive pixel shading load, allows you to customize the shading rate depending on your content. You're able to super sample, which can improve the visual quality where you need it. And it works at screen space and is very simple to integrate, as we'll get into. For a little bit of a diagram of how you can use the variable rate shading, this example shows a racing game. And in general, the horizon area that you're looking, you'll want to render at a high resolution because that's where the user is going to be looking. But areas that are, say, closer to the road and are going to be moving very quickly, because of that blur of the movement, you don't need to render it at the full resolution. No one's going to be able to see that. So you can render it at coarser shading rate, lower resolutions. In this example, the yellow regions are 2:1 and 1:2, half shading rate. And then the purple regions are 2:4 or 4:2. This diagram presents a little bit how the foveated rendering works with variable rate shading. Your fovea is the middle of your viewing. So variable rate shading and foveated rendering is a technique for improving graphic performance. This dark blue region in the center with the cross would be your foveal region, and that's where you would want to render at super sample to increase resolution. And really your foveal region is only about 5 degrees of your vision. So it's pretty small, and that's where you really want to concentrate because over half of your cones for vision are located in that foveal region. Half of the optic nerves are there. In the turquoise or teal colored area, that is what we would call the blend region in between your foveal and peripheral region. And you'll want to have some sort of intermediary resolution. And then the red shaded region of the screen would be your peripheral vision. And that is where you can lower the resolution without having any noticeable visual effects for the user. And that'll increase performance. Now, let's talk for a second about fixed foveated versus dynamic foveated. Fixed foveated rendering has been around for a couple years in VR. Generally, you'll find it on mobile GPUs because of the tile-based rendering. And that works by only lowering the resolution on the edges of the screen and increasing or keeping the full resolution in the center of your screen. But if the user looks to the sides of the lenses, they will quickly notice the lower resolution. Now, dynamic foveated rendering works by requiring eye tracking, and it updates the foveal region as you look around the screen. And this is true, real foveated rendering. When you're setting up foveated rendering, there's a couple presets that we provide. These make it quick and easy for you to get set up. If you are interested in integrating foveated rendering, you might start with, say, the narrow preset if you would like the most performance. Or if you're less worried about performance and are trying to super sample, you might choose the wide preset. And depending on your content, you might find that the balanced middle preset works best for you. And this is something that I suggest you test and tweak for depending on your content type. Let's talk a little about the performance benefits of foveated rendering. This graph is provided by the NVIDIA blog. Your performance gains will depend on the content. Variable rate shading operates primarily on the pixel or fragment shaders. So the more computationally complex the pixel shader is, the greater the potential gain. So this depends on your content. This won't have a lot of effect on vertex shader load, but for pixel or fragment shaders, you can expect to see significant performance gains up to 30–35%. Let's get started with how to integrate foveated rendering. In Unity, one of the first steps is to make sure your project is virtual reality supported. You can find this setting in your XR settings of the project settings. And if you're interested in using the foveated rendering, you'll also want to add the use_sranipple scripting define symbol. This is a using directive that lets the foveated rendering plugin know that you will be using eye tracking with it. Depending on what version of Unity you're using, you may also have to go into your package manager and enable OpenVR Desktop and install it. Next, you'll want to import the plugins that we discussed downloading earlier. You'll want to start with the Vive SRAnipple, the eye tracking plugin. And if you're adding foveated rendering, you'll also want to import that plugin from GitHub or the Unity Asset Store. Once those plugins are imported into your project, you'll want to attach the eye tracking framework, SRAnipple eye framework, to your camera. You will also want to attach your Vive foveated rendering script to the camera. And you'll want to make sure that enable eye is checked in the eye framework. And really, that's it. If you want to get started with eye tracking and foveated rendering, those steps are what is required to add it to your project and get started. And so we've tried to make this simple and seamless and easy for developers to get started. Now, if you're interested, you can also customize the settings for the foveated rendering. You'll want to check the manual adjustment box. And after that, you can change the pattern presets and the shading rate presets. The patterns are the sizes of the foveal, blend, and peripheral region. And that's where you can set either narrow, wide, balanced, or your own custom sizes. And you can do that with setting each of the region radii. You can also change your shading rate preset. You can set this to high performance or high visual quality, depending on your content, or you can customize the inner, middle, and peripheral shading rates, depending on your content. And generally, the inner shading rate, you'll want to leave at normal 1 pixel resolution or super sample. And the middle and the peripheral shading rate is what you'll want to coarse shade at lower resolutions. Now that we've talked about integrating foveated rendering in your project, let's talk about another useful case, which is recording eye animations. We talked about the Unity Runtime Animation Recorder plugin earlier. You can download that from GitHub and copy this folder of scripts into your project. And then you can attach the Unity Animation Recorder script to one of the avatar heads. We provide some avatar heads with the eye tracking SDK. You can then set a path and file name to save the animation file. You'll then want to put on the headset, click your record shortcut, and start moving your eyes around. And then click the stop shortcut. And that will generate an animation file in Unity, which you can then attach to the head avatar. And you can also disable the recording script once you're done with it. And you can click play, and that will show these animations that you recorded. And this is a quick and easy way to animate character eyes and make characters in your games or your content more expressive without having to hire an artist to manually animate, which can be expensive and time consuming. Now we'll talk about some of the APIs that are available to the developers using this SDK. One of the important ones is checking the status of the eye tracking framework. It's important, especially if you are using this to record any sort of data for any sort of research, anytime where you really care about the accuracy of the eye tracking data, it's important to make sure the status is working. Another useful API is check focus. We provide the focus API to let you know what object in the scene a user is looking at. This will work for any game object in the scene that has a collider on it. Obviously, using eye tracking and being able to tell what objects the user is looking at can be very helpful. It's also worth noting here that we first check the combined gaze of both eyes, and if that doesn't work, we also will check the left and the right eye individually in case one of their or both of their eyes are closed. And this sample just updates the name of the game object that you're looking at. Besides telling what the user is looking at, the other important API functions are pupil diameter, pupil position, and eye openness. These can be helpful depending on your content to measure the diameter change in users' eyes. This can be important for emotional responses. Pupil positions can be useful if you're measuring where the user is looking and where their eyes are in the headset. And eye openness can be used to track how open or closed the eyes are. And this is presented in a float value from 0 to 1, 0 being closed, 1 being fully open. And you'll be able to get this data using the get eye data and get verbose data API calls for either the left or the right eyes. Now we'll show a couple demo videos of some of this in functions live. This is the calibration process. You can get to it from the Steam VR Compositor menu, or it can be launched separately. The first step is adjusting the headset. The second step is adjusting the IPD knob. And the third step is following the dot with your eyes. And like I said before, if you're doing this, you don't need to move your head. You are simply moving your eyes to look at where the dot goes. And once that's completed, you've successfully calibrated. And you'll notice that the dots around the screen light up as the user looks at them. Another useful feature is the pupil position. You'll notice here, this is one of the avatars provided with the SDK. And it's also worth noting, you can see some of the blend shapes of the eyebrows moving depending on where the eyes are looking. This is demonstrating the eye openness. You can accurately track if the eyes are open or closed or squinting somewhere in between. This is demonstrating the eye focus. This is lighting up the lights based on where the user is looking. Some of the other functionality provided in the SDK is a gaze ray. Obviously, you will not want to use this in the public build version of your content, but for testing and debugging, it's great to be able to see where the user is looking. If another useful use case is adding a reticle, and an easy way to do that is to just add a sprite to the end of the gaze ray. And here's an example of some of the data running in the SDK. This is sort of a little test app that simply shows the pupil diameter, position data, eye openness values, the status of the SDK, and also the focus API of what the user is looking at. It's important to note these values are provided for both the left and the right eye. Here's another example of scrolling with eye tracking. You can use this for text or menus to smoothly and easily scroll the screen as the user gets to the end of the content. So in this example, when the user is reading lines at the bottom of the screen, it will smoothly scroll to the next line. And you can also scroll back up. Let's talk briefly some of the tips and best practices when developing for eye tracking. The pupil diameter data is provided for the left and the right eye individually. Generally, it's best to measure relative changes in pupil diameter. That information can be very useful. First person viewpoint is better than third person for eye tracking uses. Generally, it puts you in the proper perspective and objects will be larger. If you are adding gaze aware to small objects, it can be helpful to increase their collider size to make it easy for the user to focus on them. If you're working with UI elements and buttons, be careful with strong outlines or any elements that may be near the button but draw the user's vision away from the center. Those can distract. And also on UI elements, if there are labels, it's important to group the label with the button. And so if the user is reading the label, you can also treat it similarly. Also, if you're using colliders for complex shapes, it will be best to use a mesh collider. If objects are near or blocking other objects, the mesh collider will fit it better and you'll have more accurate results. Now, if you're interested in learning more tips and best practices, if you have any questions or issues or bugs, I will suggest checking out our forums. We are very active on our developer forums. We have engineers there to help with any issues. We're listening to your feedback and always looking to improve our SDKs and documentation. So please register and join and check out our forums. If you have any questions, you might find some useful answers there. These are our forums, very useful resource. And now we will have some time for Q&A. If you have any questions, you can type them in the chat and our moderator will send them to me. We got a question about if a participant wears their personal vision correcting glasses, does that affect the accuracy with which we identify the pupil size, since it can affect the recording by reflecting the infrared illumination? That's a great question and a common one we get. So you can use glasses with the eye tracking and the Vive Pro Eye. In our tests, it has not affected the quality of the eye tracking. I personally wear glasses. I generally don't need to wear them in VR, but I have tested and experimented with it and haven't noticed any changes in the results. We've also had a number of users test with glasses with eye tracking, and it's worked for them. Another interesting question is, does Vive Pro Eye work with wireless? And yes, the Vive Pro Eye, we have a wireless transmitter that's available for PC, and the Vive Pro Eye works with that. It's also important to note what the gaze data output sampling frequency is, and that's 120 Hertz for the eye tracking SDK. It's worth noting that the Unity game engine main thread will only run at 60 Hertz. So you will want to create a separate thread if you're interested in gathering data at 120 Hertz in Unity. And if you would like some samples on that, we provide those in the forum. Another question is about, does the Vive Pro Eye work with the Tobii SDK? And yes, we work with the Tobii SDK. They're a great partner. And there is certain functionality that, depending on your use case, you might need from the Tobii SDK. The Vive Pro Eye tracking SDK does have a lot of uses, and you can integrate your own analytics package if you would like, but it does not come with a built-in analytics package. That is functionality that is provided by the Tobii SDK, including access to the raw camera images and video if you would need that. Another question is about, can the calibration data be saved for users? And currently, no. In general, the best practice is that any users, every time they put on the HMD, will be put on slightly differently. So if you need high accuracy and you really care about the quality of those results, you'll want to run the calibration for each user. Now, if you're just demoing some game content and the accuracy doesn't need to be 100% the best it can be, then you don't necessarily need to calibrate for every user, but we recommend it. Another question is, do AMD GPUs support foveated rendering? And currently the answer is no. We're working with an AMD to better support foveated rendering, but currently it requires the variable rate shading plugin, which is only provided by NVIDIA. Another helpful question is, what happens when using a regular Vive Pro with Vive Pro Eye content? And the answer is, if you use a regular HMD instead of a Vive Pro Eye, it will simply just fall back to assuming your eyes are looking forward in the center of the screen. And we'll wait another minute or two in case there's any other questions. If there's no other questions, we're going to wrap this up. If you are interested in this, please download our SDKs and plugins. Please join our forums if you have any other questions that weren't addressed here, or if you're interested in this technology. Reach out on our forums. Lots of useful information and always happy to help there. Please stay tuned for future webinars. We will have a survey at the end of this for your feedback, which we would appreciate. And thank you so much for joining today.